In this video, we're going to take a look at how to solve a certain class of differential equations known as separable differential equations. We're going to say that a differential equation is separable if we can write it in the form y prime equals f of x times g of y. The term separable here refers to the fact that on the right-hand side of this equation, we can separate our variables into a function of x multiplied by a function of y. As we will see soon, if we have a separable differential equation, then it can be solved in a pretty straightforward manner, assuming the functions f and g are nice enough to be able to integrate appropriately. It's also important to note that not every differential equation will be separable. And so in order to use the method for solving separable differential equations, we first must recognize that our differential equation is separable. That is, it can be written in this form f of x times g of y. Here are 4 examples of differential equations, and we'd like to identify which ones are separable and which ones are not. And for those that are separable, identify the functions f and g from the definition. The first equation, y prime equals the quantity x squared minus 4 multiplied by the quantity 3y plus 2, is already written in the appropriate form that we need to determine separability. The first function here is a function of x. We have x squared minus 4. There's no y involved there, so that's a function strictly of the variable x. The second factor, 3y plus 2, is a function of y only. There's no x involved in that term. And so this equation on the right-hand side is already given to us in this form of a function of x multiplied by a function of y, and so this equation is separable. The second equation, y prime equals 6x squared plus 4x, has no y at all on the right-hand side. And so whenever we have just one variable, our differential equation will automatically be separable, because here we have a function of x, and if we'd like to make it formal, we could multiply that by 1 and think of the constant function of 1 as our function of y. And so this will be our function of x, 6x squared plus 4x, multiplied by our function of y, 1, and this one is separable as well. The third equation, y prime equals xy plus 3x minus 2y minus 6, might look to be not non-separable at first. However, we are able to factor this particular equation, and if we factored this equation, we will get x plus 3, x minus 2. So this factors in sort of a natural way. We can do a factoring by grouping here and obtain x plus 3, y minus 2. Sorry, that's a y. And so here we have a function of x multiplied by a function of y. And so this particular equation is separable as well. The last one, y prime equals e to the negative y plus x squared. We have to be a little careful here because we do have a sum of a function of x and a function of y, but not a product. And there's no algebraic way to write this as a product of a function of x and a function of y. And so this one turns out to not be separable, unlike the first 3, which all are separable. Once we have a separable differential equation, solving it is just a matter of actually separating the variables and integrating. So here we're going to show the process of solving a separable differential equation in general, that is of y prime equals f of x times g of y, and then we'll look at an example where we'll put this procedure into use. So in order to solve this equation, the first thing that we're going to do is rewrite the derivative as dy dx. This, of course, doesn't really do anything. It's just a different notation for the derivative, but it will allow us to think of dy and dx as separate entities. Even though that is not actually the case, dy dx is a single symbol that represents the derivative, this notation makes it appear to be two different symbols, dy divided by dx. We can now rewrite this equation so that all of the x terms are on one side and all of the y terms are on the other. In particular, we could rewrite this as dy over g of y equals f of x dx. So here we're multiplying both sides by dx and dividing both sides by g of y. And now on the left-hand side, everything, including the differential, is in terms of y, and everything on the right side is in terms of x. We're now going to integrate both sides. Now, once we do this, on the left-hand side, we'll have a function of y, and on the right-hand side, a function of x. And if possible, the next step would be to solve this equation for y. And if we are able to do this, this function of y will be our solution to our differential equation. At this point, we could then check for the initial condition if we have one, and then use this to find the particular solution that we're looking for. So now we'll take a look at how to use this approach in an actual example of a separable differential equation. In this example, we want to solve the initial value problem y prime equals x squared over y squared with the initial condition y of 0 equaling 2. The first thing is to note that this is a separable differential equation because we can write this x squared over y squared as x squared multiplied by 1 over y squared. And by doing that, we're able to separate our variables into a function of x multiplied by a function of y. We're also going to rewrite y prime as dy over dx so that we have our differentials for both variables in our equation. Our first step then is to rearrange this equation so that all of the y terms are on one side and all of the x terms on the other. So if we multiply by y squared, we'll have a y squared dy on the left side. And if we multiply by by dx, we're going to end up with x squared dx on the right side. And so this is our separation of variables. We're putting all of the y's on one side and all of the x's on the other. Once we have it in this particular form, we're going to integrate both sides. And here that is easy to do because these functions are nice enough that we can easily anti-differentiate them. So what we get here is y cubed over 3 equals x cubed over 3. Now, because these are indefinite integrals, we do want arbitrary constants here. And so one thing we could do is, for example, add a c1 on the one side and a c2 on the other. But because these are just arbitrary constants, we could then at this point subtract c1 to the other side. And so we end up with something like this. And now c2 minus c1 will be an arbitrary constant because it's the difference of two arbitrary constants. And so we can simply make that just one constant c. And so this is something that can always be done with separable differential equations, is we could always just go ahead and put the arbitrary constant on one side of the equation. And so that's what we're going to do here. So our result is the equation y cubed over 3 equals x cubed over 3 plus c. At this point, we want to solve for y. And so to do that, we can multiply both sides by 3. And so we get y cubed equals x cubed. And again, we have a game we can play with this constant. Technically, it should be 3 times the arbitrary constant c. But if I take an arbitrary constant and multiply it by 3, I again will get an arbitrary constant. And so here we can just absorb that 3 into our constant to make the equation as simple as possible. So we have y cubed equals x cubed plus c. To find y then, we just take the cubed root of both sides. And so y equals the cubed root of x cubed plus our arbitrary constant c will be our general solution to our differential equation. Now we do have the initial condition to consider here, y of 0 equals 2. And so we want to find the value of c that satisfies that initial condition. And so we'll substitute in 0 and 2 for x and y. And when we do that in our general solution, we get that value of y, which is 2, will equal to the cubed root of 0 cubed plus c. And so here we get 2 is going to be the cubed root of c. And cubing both sides of this will give us that c is equal to 8. And so we have our general solution, y equal cubed root x cubed plus c. We have our particular solution for this initial value problem by setting c equal to 8. And so our solution to our problem is y equals the cubed root of x cubed plus 8. And this is a basic example of using the method of separation of variables to solve an initial value problem.